Let's now take a look at computation of moments of SDEs. As in the derivation of the Fokker-Planck-Kolmogorov equation, let's use the Ito formula for phi of x and t, where now phi also depends on t. So if we use the Ito formula, take the expectation and formally divide by dt, we get the following differential equation. So the time derivative of the expectation of phi is equal to the expectation of the partial derivative of phi with respect to time, plus the summation of expectations of the partial derivatives of phi with respect to xi times the corresponding fi's, plus half times the expectations of the partial derivatives of the phi with respect to xi and xj times the corresponding elements of L, Q, L transpose. This formula can now be seen as a general moment differential equation for the corresponding SDE. If we now select the function phi to be equal to xu, where u is one of the indexes, then we get that the time derivative of the expectation of xu is equal to expectation of fu. So in vector form, we can write down the mean differential equation like this. So the time derivative of mean is equal to the expectation of f, x and t. In order to derive the covariance differential equation, we can select the phi to be equal to xu xv minus mu mv, where u and v are two indexes of x, and the means mu and mv are also allowed to depend on time. Substituting this into the general equation gives that the time derivative of the expectation of xu xv minus mu mv should be equal to the expectation of xv minus mv times fu plus the expectation of xu minus mu times fv plus them the uv element of the matrix LQ L transpose. Thus the final mean and covariance equations say that the time derivative of mean should be equal to the expectation of f xt, and the time derivative of the covariance p should be equal to the expectation of f times x minus m transpose plus the expectation of x minus m f transpose plus then the expectation of LQ L transpose. Now the catch in these equations is that the expectations are with respect to the distribution p, x and t. And the reason why these equations are not so useful is exactly that. So in order to solve this equation, we need to know the distribution p, x of t, which in turn is the solution to the Fokker-Planck equation. So we actually cannot solve these equations without solving the Fokker-Planck equation. However, in linear Gaussian case, the first two moments already characterize the whole solution and the distribution px of t. So in that case, we can indeed use these equations to solve the mean and covariance. And this is also a useful starting point for Gaussian approximations of SDEs. Let's now take a look at an example of mean and covariance equations, or actually mean and variance equations. The Erskine-Uhlenbeck process is given as dx is equal to minus lambda x dt plus d beta, and we now assume that the x at 0 is equal to x0. So in this case we have a one-dimensional state and f of x is equal to minus lambda x. Thus the differential equations for the mean and variance are given as the time derivative of m is equal to minus lambda m, and the time derivative of p is equal to minus 2 lambda p plus q. So these are the result of substituting f of x to the mean and covariance equations. So in this case we have a closed set of equations for both mean and covariance, and we don't actually need to explicitly solve the Fokker-Planck-Kolmogorov equation first to write down the differential equations and even solve them, because the differential equation is linear. In this case, the state distribution or the distribution of x is given as so p of x and t, which is also the same as p of x as function of t. It's a Gaussian distribution with mean mt and covariance pt. So this distribution would actually also solve the corresponding Fokker-Planck-Kolmogorov equation. Using the generic moment differential equation it is also possible to derive differential equations for the higher order moments of SDEs. By higher order moments, it's meant the higher order polynomial moments in this context. But the computational complexity becomes high because with state dimension n, we have n to the power of 3 third order moments, n to the power of 4 fourth order moments, and so on. Recall that the mean has n elements, covariance n to the power 2 elements, and so on. So this is the generalization of that. However, we can write down the equation still. So recall that the given scalar function phi of x, where x is scalar, satisfies the following differential equation. So the time derivative of phi of x is equal to the expectation of the partial derivative of phi with respect to x times fx plus q over 2 times the expectation of second derivative of phi times L to the power 2, where we have assumed that the stochastic differential equation is dx is equal to f of x dt plus L d beta. If we now apply this result to the function phi of x is equal to x to the power n, we will get that the time differential of the expected value of x power to n is equal to n times the expected value of x power to n minus 1 times f plus q over 2 times n minus 1 times the expected value of x power to n minus 2 times L squared. So of course the first n comes from the first derivative and n times n minus 1 comes from the second derivative. This in principle is an equation for the higher order moments. But the problem is that the expectations are with respect to the Fokker-Planck-Kolmogorov equation, and actually to compute the expectations at order n will generally need the results from the expectations from the order n plus 1, and the set of equations is not closed. So to actually use these equations, we need to somehow cut the number of moments that we consider, and that kind of methods are called moment closure methods.